So section 2.7 is going to discuss function notation. We're also going to look at domain and range a little bit. But let's start out with a nice little graph and some function notation. So you've got a graph of g of x, which is right here, and a graph of f of x, which is below that. And they ask you to do some calculations. And I kind of like this problem because it's just a simple way of asking, do you understand this notation? So this notation really can be almost distributed. It's not quite distributing, I guess, but it's really the equivalent of f of -1 plus g of -1. And to find those values, you're going to look at the curve for f, you're going to look at the curve for g, and then try and approximate those things. So for instance, let's see, I'm going to assume that that's my axis. So f of -1 is going to be right there. What's the value of f of -1? What would you assume that's going to be? Let's round it to the nearest integer. F of -1, that's here. It looks like about 1 to me. How about g of -1? What would g of -1 be? Any takers? Come on. Someone help me out here. 4? 4. Yeah, it'd be about 4. So 1 and 4 gives me 5, and that's the same as f plus g at -1. So it's just some notation that I'm trying to get you familiar with here. Likewise, this notation would be something like this, f of -1 minus g of -1. So we're just flipping some signs here a little bit. That's going to be 1 minus 4, which would be -3. You can keep on doing this down to this one. What do you think is going on here? F of g? Oh, f times g? Well, it is f times g, so this would be the same thing as f of -1 times g of -1. Unfortunately, we're dealing with the same point, so we'll just multiply those together and get a 4. The last one, again, this is just more notation, really stands for f of -1 over g of -1. I can't say that I use this notation all that much. I try and use this kind of stuff to be a little bit more straightforward, but you will see this stuff in WebAssign. So the last one's going to be the same as 1 over 4 or 0.25. I typically prefer fractions rather than decimals. If I really care about something, then I'll say, round to this many decimal places or give me an answer as a fraction, etc. But in absence of that, you're free to give me a fraction or a decimal. Doesn't matter. Now that same idea where we're kind of distributing here applies to stuff like this down here, where we've got f of x is 3 minus x squared, and below that we've got g of x. G of x is x squared plus 4, and they're going to ask you to run through all these different calculations. So let's start with f plus g of x. So this example B here. F plus g of x. Well, it's really the same thing as f of x plus g of x. F of x plus g of x, well, it's going to be 3 minus x squared plus x squared minus 4. Can anyone simplify that for me? How does that end up? What do we get there? Anything? Is there any simplification? Can we do that much? Lip? Any simplification there? Like terms or something?
Terms, yeah.
So what do I get when I simplify all this? What happens to these two terms? Those cancel each other out. That's good. Let's keep going. Is there anything else that I can combine?
The 3 and the negative 4.
Yeah, 3 and negative 4 give me negative 1. So no matter what you're at, when you're adding these two things together, you're going to end up with a negative 1. So, okay, let's take a look at it graphically. And actually, it's kind of interesting to see that Desmos understands this result as well. So, let's see, this is 2.7. There you go. Here's your f of x. You've got a parabola that faces down. Here's your g of x. You've got a parabola that faces up. But when you add f of x plus g of x, you just get this. You just get negative 1. So it doesn't matter what value of x you're at, you're going to get that negative 1. So, nice. Nice. Okay, let's do a couple more here. The other thing that they ask is f minus g of x. So it's going to be f of x minus g of x. When you're subtracting, you got to be a little bit more careful. So let's be careful on that. F of x was 3 minus x squared minus g of x, which is x squared minus 4. There's one thing I did that is going to help you out if you take the time to do it for yourself. And that is I put this in parentheses. Why do I care about the parentheses? Why am I putting it in parentheses? Blake, seems like you got an idea that's right there. Why am I putting it in parentheses? What difference could that make? Well, let's see. How about if I write it without parentheses? Does that work for you? What's wrong here? What I miss? Jude? Yeah, that negative has to distribute itself to both terms. So I distributed the negative to the first one, but not to the second one. So this should be a plus here because that negative has to distribute. And that's what's easy to miss on these things, which is why I try and help you out by putting in that parenthesis. But this has to distribute itself to both terms. Thank you, gentlemen. Now, after I distribute that to both terms, I can collect like terms. What do I get when I collect like terms? Zandos? What do I get when I combine the like terms in this one?
Minus 2x squared and 7 plus 7.
Nice. What if somebody wrote 7 minus 2x squared? Should I mark them wrong? No. You guys are soft. Nah, I'm kidding. No, this is fine. It doesn't matter which way you write it. Typically speaking, though, you would write it the way Zandos gave it to me, minus 2x squared plus 7. You're going to put these in decreasing orders of magnitude or powers of the exponent. So an x squared, then an x, then a constant, that kind of thing. Because as we'll see later on, this tells me a lot about our graph. For instance, it opens down, it's going to open a little bit narrower, and it's been shifted up by 7. So there's a lot of information you can get out of that. Let's take a look at a different one. So how about if we try f times g of x. So that's going to look like 3 minus x squared times x squared minus 4. What do I have to do in order to figure this one out? Stan, any suggestions?
You gotta multiply them out.
Yeah, got to multiply them out. The 3 has to multiply both terms here. So you're basically distributing 3 times that, 3 times that. And then you got to do likewise with minus x squared and distribute that to both terms in the second binomial. So what's that going to give me? Any suggestions? What do I get there? Dominic? Any suggestions? What do we get? Let's start together with the first term. 3 times x squared. That's pretty self-explanatory just about. 3 times what? What am I multiplying here? Multiplying 4 or negative 4? Negative 4. Thanks, Max. How about the middle term? A minus x squared and an x squared. So, first of all, what sign do I get here? What should I put down? A plus or minus? Negative. And it works out the same if you add them or multiply them. But what happens when you multiply things with the same base? Do you add the exponents or do you multiply them? Add them. Good. So, not that I'd be able to tell that you did one versus the other in this example, but yeah, you want to add them. And last but not least, a minus times a minus is a plus, 4x squared. Still got those like terms. Be a hero and put this in descending order and also combine the like terms. Perhaps I should say be a hero or heroine.
X to the power 4 plus 7x squared minus 12.
Plus 7x squared minus 12. Somebody put the plus on that A. It'd be a negative here, right?
Oh my gosh. Yes,
Agree?
it
Okay. All right, cool. Thanks so much. And last but not least is f divided by g of x. So let's do that one, finish out this example. There's something a little bit peculiar about this one. F divided by g of x. It's really going to be f of x divided by g of x, which in our case is going to be 3 minus x squared divided by 4 minus x squared. And the last one comes with a little extra work here for us. We need to find the domain. What is the domain? Well, the domain in these other ones is just all real numbers. There's nothing in this kind of a polynomial or this one that prevents you from putting in any value of x. But there are a couple values of x that are going to cause problems with the last one. What could go wrong with the last one? What could happen depending on your values of x? Yeah. If this was a 0, you'd be dividing by 0. That's a mathematical no-no. That literally stopped a, I'm not trying to remember if it was an aircraft carrier or a battleship. One of the two. One of the computer programs running their nuclear engines, nuclear-powered engines, branched to someplace that there was a division by 0, and it shut it down. The ship had to be towed into port. It took them 3 days to fix it. So, anyways. Division by 0 is not a good thing. So let's see if we can't avoid that. Where is this equal to 0? Where does 4 minus x squared equal 0?
2.
Good. Keep going.
Minus
2 and negative 2. Now I'll show you two different ways you can work on this. One, if you move that to the other side, you get 4 equals x squared. Now when you take the square root on both sides, it's not enough just to take the square root. You got to take plus or minus the square root. So let's be emphatic about that. Plus or minus. That's going to give you a plus or minus 2 for x. So that's one way to do it. There's another way to do it. You can factor it. You can say, all right, well, that's 2 minus x times 2 plus x equals 0. Where does this equal 0? Well, one possibility is when x equals 2. What's the other possibility? When x is minus 2. So you're getting the same thing either way. But be careful. That's not the domain. These are the points that we want to avoid. So let's put those on a number line for ourselves. Just kind of a small one here. And negative 2 and 2. Let's put little hollow dots on each of these. We don't want those points. We want everything else. So in terms of interval notation, which is likely what WebAssign is going to ask for you, let's see. What would this first interval be? Lena?
Oh, minus infinite, comma, minus 2 in parentheses.
Nice. And then -2 to 2, union 2 to infinity, all with parentheses. So that would be your answer. That would be the domain in interval notation. If I didn't specify interval notation, you could probably just write x is not equal to 2 or -2 and get away with that. But likely you're going to have to put it in interval notation. Awesome. Awesome. So a nice review of domain there a little bit and some interval notation. Let's move over and take a look at some more of these types of problems. In particular, I'm going to be interested in looking at the domain of some of these functions. In fact, let's start out by finding the domain of f and g for this example. So this is example C. F of x equals square root of 16 minus x squared, and g of x is the square root of x plus 3. In general terms, what could go wrong when you're working with a square root? In terms of we put something in and it doesn't work, well, what kind of problems could we run into in working with a square root? Can I take the square root of any number? Not negatives, right? So what I want from this is I want to make sure that they're positive, or at the very least, what? 0, right? So I want to make sure that these are greater than or equal to 0. So that means for the domain, I want x plus 3 to be greater than or equal to 0. That means x is greater than or equal to -3. Okay, that's my domain for this one. The domain for this one is going to be a little bit more work. Now, I guess it depends on you and, you know, how comfortable you are with some of the stuff, but we'll go through it thoroughly. I have the same requirements for the domain here that I had just a minute ago. I need to make sure 16 minus x squared is greater than or equal to 0. Nice. All right. Well, how are we going to do that? We can't just move these to the side and take the square root on both sides. It won't work. So there's a couple things you can do. Can anyone factor this and tell me where this is actually equal to 0? How would this factor? We did one like just a minute ago. The 4 minus x squared was 2 minus x and 2 plus x. How about this one? How's that factor? 4? All right, so 4 minus x and 4 plus x, right? The only place that this can change sign is where this actually equals 0. By the way, what would the graph of this look like? 16 minus x squared. Can anyone tell me what that graph would look like before I pull it up on Desmos?
Upside down parabola?
Yeah, upside down parabola. And there it is. In fact, you can see these points where the function crosses the x-axis. They're exactly where Aurora predicted them, at 4 and -4. So looking good there. But what we want to know is what values of x that you put in here that make this product greater than or equal to 0. So there's a couple ways you can do this. One of the ways I was suggesting that you use on exam was something like this. You find these points where it's actually equal to 0, and then you test points in between. So this would be the interval negative infinity to -4, -4 to 4, and 4 to infinity. I need some test points for each of these intervals. What's a value to the left of -4? You don't have to think too hard. You don't get bonus points for giving me a crazy number.
-5.
-5,
And 5.
2, and 5. Sure. Now if I put in a -5, I'd have 4 minus -5 is 9, because the double negative becomes a positive. So I'd have 9 times -1. That's negative. What if I put in a 2? I'd have a positive times a positive. Positive times a positive has to be positive. And then the last one here, if I put in a 5, 4 minus 5 is -1 times 9. It'd still be negative. So negative, positive, negative. You don't necessarily have to do that by plugging in points. This is really convenient, especially if your graph is really ugly. But you know what the graph of this looks like. And in this case, at least, it kind of matches what we expected, right? To the left of -4, it's negative. Between -4 and 4, it's positive. And to the right of 4, it's negative. So we get the exact same conclusion if we were looking at the graph. So what do I want for my domain then? Which interval or intervals is going to be my domain?
-4 and 4?
Yeah, -4, 4. I want to know where this thing is positive. So that's going to be my domain. So our domain is -4 to 4. So if you're following along on Desmos, you can do that pretty nicely for this example. Let me go back here. And let's take a look at this graph. There you go. In fact, this graph looks like what? What would you describe it as? Top half of a circle, maybe? Yeah, top half of a circle, radius 2. This is exactly what it is. And let's take a look at this next graph. Now, before I look at that next graph, can you confirm what the domain is? Did we get it right? Yeah, -4 to 4, that's where this function lives, all right? Outside of that, it's not defined. That's okay. Let's shut that one off, turn this next one on. The next one is our other graph, and that started at -3. Oh, okay. That looks pretty good. Now, what they ask you for in this first example is, well, what's the domain of f plus g? Now, I use different names here, but here's that function. Is that defined from -4 to 4 anymore? Is it defined from -3 to infinity? No. Let's understand how and where this thing is actually defined. So to do that, let me take a look at our domains. This one is domain from -3 to infinity. Let me give these some colors here to try and help things out. So this one, I guess, a nice blue here for you, and salmon here for you. Let's draw these graphs on the number line anyways. So the first one is defined between -4 and 4. Okay, so let's see here, -4 to 4. Let's put in a little -3 here as well. So the first one is going to look like this. Solid dot here to here. That's the domain of the first graph. Let's take a look at the domain of the second graph. The domain of the second graph has a solid dot here, and it goes to the right. where are these both defined? Where's the function defined in both cases?
-3, 4.
Yeah. So the overlap right here, that's your new domain. So the domain of f plus g is -3 to 4. It's where they overlap. And that's kind of in the orange. Now the nice thing about your graphing calculator or Desmos, if you did something like this, if you put those two functions together, you would only see it graphed here to here, because that's the only places where it exists. To the left of -3, the first function is not defined, f is not defined. To the right of 4, excuse me, to the left of -3, the second function is not defined. To the right of 4, the first function is not defined. So, okay. If you look back at this graphically, notice that it's defined at -3 all the way up to +4. Beautiful. Beautiful. All right, that's a good one. So let me pause here. If there's something that's you're a little bit uncertain about, now's a good time to get some help. Yes, please.
Why can't we square root the 16
You mean get 4 minus x or something like that?
Yeah, or what if you just move the x squared to the other side and then square root both sides?
You can, but that would only give you one solution. It'd give you 4 is greater than or equal to x. And yeah, there's two parts of this. There'd be the 4 greater than or equal to x, and x is greater than or equal to -4. You really only get one out of that. So there's a couple ways you can work this one, but moving the x squared to the other side and taking the square roots doesn't really give you what you expect. Yes?
On that,
Liv?
then, on example B, we did basically the same thing, but then we just added the plus and minus in front of it. Or how did we do that?
That's because we had an equation, not an inequality.
Okay.
Yeah, an inequality gets a little bit messier. So an equation, yeah, no problem, do that all day. But inequalities, it gets a little dicey. And I mean, you can kind of make it work if you abuse notation and some rules of math, then you can make it work. I'm not happy to see it though. All right, good question, appreciate the questions. Anything else on this? Let's finish up a couple more here. There's f times g of x. So it's basically just some more notational work here. Yeah, I guess I'll do that one here. We can do both. Example C.
Dr. Barron,
Yes.
I have a question.
Yeah, please.
So in the last example we did, f plus g, right?
Yes.
I think one of them is -3 to infinity, and it's solid dot, right?
Yes, right here.
And why we use break when we use domain if one of them is like solid dot?
Well, it has to be defined for both parts of the function to be defined as part of their sum. So the only place where it's defined on both ends is in between these points. Because to the left of -3, g of x is not defined. You'd be taking the square root of a negative number.
So solid dot does not mean anything, so it doesn't matter.
Solid dot, well, it kind of does matter, because if this was a hollow dot, in fact, I've got a nice example that addresses exactly what you were talking about, all right? And that's going to be the last one we do for part C here, but it has to be defined on both cases. Now, g of x is defined for -3, and so is f of x. So these two overlap there, that's why you're getting a solid dot here and a bracket here. Likewise at this endpoint, they're both defined, so that's going to be in the domain of the whole thing. But that's not always going to be the case. So if I can ask you for your patience for just a minute, when we get to the domain of this one, you're going to see a little bit of a difference. So let's see, example C, continued f minus g, really that's f minus g of x for f of x minus g of x. In this case, that's going to be square root of 16 minus x squared minus square root of x plus 3. Great. And that's it. The domain is going to be the same as it was, so nothing new and exciting there. You can do likewise with multiplication, but let me get to the division one, because that one has a little something interesting going on. Now they just write it as f divided by g. Keep in mind what that really is f divided by g of x, or better yet, f of x divided by g of x. Well, that's going to be square root of 16 minus x squared divided by square root of x plus 3. We still have the same domains for f of x and g of x, except there's a little bit more of a problem with this one. There's something else that can go wrong. What else can go wrong? Somebody's whispering it. Go ahead.
The denominator could be 0.
Yeah, the denominator could be 0. Where is the denominator 0 in this function? Ella? Minus 3? Yeah, minus 3. 1 second, please. I don't know why he had to call me out of class for that one. It wasn't, I was thinking, oh, it's some kind of emergency, etc. So my apologies here. Yeah, we want to avoid having a 0 in the denominator. Now, in our first part of this problem, both of these functions were defined between -3 and 4. But now that we've got this crazy denominator of g of x is the square root of x plus 3, we can't put in the -3. So how does that change our domain? How does that change our domain if I can't use -3 anymore? Yeah, it means a parenthesis there. So the domain is going to be -3 to 4. I can use a 4. Nothing wrong with a 4. It gives me a 0 here in the numerator. That's okay. You can divide into a 0. You just can't divide by a 0. If you take a look at the graph, you can kind of see what's going on there. So let me shut off this one and turn on this one. There's your graph. It's defined at 4, no problem there. It's defined for everything. But what happens is I try and get closer to -3. The graph is just going up and up and up, out of control, out of sight. And it's not actually defined at -3. You won't see a point on this graph for -3. Okay, beautiful. All right. All right. Let's do that one again for a problem like this. So, yes, please. No, I skipped the multiply one. I mean, if you want, let's see. There you go. Here's the multiply one. F times g is f of x times g of x, like that. So that'd be the square root of 16 minus x squared times the square root of x plus 3. And if you really wanted to, you could make that one big square root. 16 minus x squared times x plus 3. You know, there's a part of me that's nervous about that last step. This much you can do at least. Next step, Yeah, this next stuff, I don't think I would go there because I think that might actually change the domain there. So this part is good. That part, I think I have to get back to you on that. I think you just got a bigger domain there. Okay, but the notation here was really what I'd be looking for as part of this problem. Let's take a look at D. Your chance to decide, did you pick up what I wanted you to out of these last two examples? Mag?
Did you say earlier that the domain of f minus g was the same as f plus g?
Should be, yeah. Let's take a look here.
So,
Let's see, well, it has the same restrictions. This is only defined between -4 and 4. This is defined from -3 to infinity. But let's take a look at it graphically, you know, just to save myself a little time. So here's our function just a minute ago that we had. Let me clean up the axes. What if I put a minus there instead of a plus? Well, it's still, I mean, it's a crazier looking function, but it's still defined from -3 to 4. So the domain didn't change. It just looks a whole lot different, doesn't it?
okay.
Yeah, no, I appreciate that. Okay. Let's take a look here. There's a lot of things that you have to kind of balance out for this one. Excuse me. So example D. F of x is the square root of x plus 5 minus square root of 8 minus x over x. So there's a lot of little parts here to this that we have to deal with. We have to figure out, well, what's going on with this part? What's the domain here? And then there's this part right here. Let me do it in orange. What's the domain of that part? And there's one last little piece here, and that is we're dividing by x. So what's the domain of, or what I have to worry about here? So there's a lot of little parts, and we want to make sure that they're all defined at the same time. If you're watching this later, give yourself a chance to try and solve this yourself. Let's take care of this thing first. What happens with this x here? What should I worry about or avoid?
0.
Yeah, x can't equal 0. So let's put a nice big little circle on the 0. We can't have that. Everything else we're okay, right? It could be positive infinity, you know, it could be all the way up to negative infinity. It just can't be 0. Great. How about this part here? Square root of x plus 5. What's the domain for something like that? Let's do that over here. What do I want to make sure of? I want to make sure that x plus 5 is greater than or equal to 0. When does that happen? Yeah, from -5 to infinity. So that's going to be this piece here. Nice. And we got to do similar for this last piece over here. 8 minus x is greater than or equal to 0. If we move the x over to the other side, that's fine. It is a little bit harder to interpret that way. X is greater, or excuse me, 8 is greater than or equal to x. You might want to spin that around. What would that look like if I flip that inequality around? If I put the x on the left-hand side and the 8 on the right-hand side. All I'm doing is I'm flipping it around. Now, I used to get embarrassed, but now I guess I don't care anymore. Saying this, the alligator eats the bigger number. 8 was the bigger number, so it should be the bigger number when we flip it around. So it's going to be x is less than or equal to 8. The advantage of having the x on the left is it's just easier to interpret. This inequality points in the direction that you're going to draw your graph when it's on the left. X is less than or equal to 8. That's everything less than or equal to 8. So let's put that in as part of our graph. So solid dot here, everything to the left. And now you got to take a look at, oh my gosh, where do all these things overlap? Well, let's see here. Where do you see them overlapping? Do they overlap here at -5? Yeah, they overlap at -5. -5 to 0. -5 to 0. Is 0 going to get a bracket or parenthesis? Parenthesis. How about to the right of 0? 0 to what? Where do they overlap here? 0 up to 8, and then again a bracket. So there's your there's your intersection on that one. Okay, looking good on that one. That was a nice, challenging one, a little bit tougher. Comments or thoughts on example D here? Good on that one? Thank you. Jude? Lena? Al? Yes? No? Okay. All right. Let's move on. Moving down to example E. This one is a graph. So they give you the graph of F and they give you the graph of G, and they ask you to try and predict what does the graph of F plus G look like. How would I do that? How am I going to figure out, if I don't have the equations and I can't plug this into my graphing calculator, how am I going to figure out what the graph of F plus G should look like? Well, I guess one thing you could do is you could look at points. For instance, if this is the graph of F and this is the graph of G, then let's see, we got 2, 4, 6. What's F of 6? What's F of 6 going to equal? That one? No takers on f of 6? It's below the x-axis, though. You're real close. Not 2, but -2. Yeah, -2. Good deal. So f of 2 is, or excuse me, f of 6 is -2. How about g of 2? Or g of 6, I should say. G of 6. G of 6 is going to be 2. So when I calculate f plus g of 6, f plus g of 6, it's really f of 6 plus g of 6. What should I get? Yeah, I should get 0. Is this graph at 0? At 6? No, it's not. So this one can't be it. Is there one that looks like it could fit that definition? Does it work so that f of 6 plus g of 6 is 0, or the graph of f plus g is at 0 at x equals 6? Is there one of these graphs that matches that calculation?
The last one?
Yeah, the last one. And let's just check one more point here. So again, you've got your g here and your f of x here. If you check one more point, I don't know, what's an easy point to check? Maybe 0, right? Let's check f of 0 plus g of 0. Well, f of 0, Ethan, what would f of 0 be, please?
1.
Good, and g of 0 is 2. So I should get a total of 3 for f plus g of 0. Is that where we're at on the graph? Yeah, that looks pretty good. So I'd say that one's the winner. You could check some more points to your satisfaction, but this one is the winner. These other two don't match what should happen at 0 or at 6, for that matter. So out of luck on that one. These two really. Flipping it over. I'll leave this one for you to play with at home. Let's move on to some different work with function notation here. This notation, I'm trying to think who was, it might have been Euler that came up with, Leonhard Euler, who was an amazing mathematician, very prolific. And what was most amazing about him is that he was blind the last 17 years of his life, and he continued to churn out all kinds of mathematical papers on a dazzling array of topics. Our use of the notation pi goes back to Euler, although he flip-flopped on exactly what that meant. But let's take a look at f of -2, or f of 2. So we'll start by finding f of 2. And f of 2, they're just asking you to take a 2 and put it in to the function. So it's going to be 4 times 2 minus 3 gives you 5. So then f of 2, if I put another f on the outside, well, that's going to mean really f of 5, right? I'm going to take that 5 here and replace f of 2 by that. And my pen is dry here, so I'll try that as a 5. What would f of 5 equal?
17.
Yeah. 4 times 5 is 20. Minus 3 is 17. Nice, thank you. This is called function iteration. When you take the output from one function, you put it back into the same function, you keep on going, it's called function iteration. It leads to some pretty cool things, more than I can discuss right now. But why don't you try the same thing with g of 3. So g of x is 5 minus x squared, g of 3. So see what you can get there. First one with the right answer gets to do an extra 10 problems of homework. Go. I'm still trying to perfect my reverse psychology. It hasn't gotten there yet, but we're getting there. What's g of 3? What's the first part right here? What'd you get?
-4.
Yeah, thank you. You get -4. So let's take that -4 and put it in here. G of 3 was -4, so g of -4 becomes 5 minus -4 squared. What do I get when I square -4 and subtract it from 5? 5 minus 16 should give you -11. Yeah. You got it? You good?
Yeah.
Okay. Nice. Now you don't have to stick with the same function. You can kind of mix and match a little bit. You can go from one function to the next. So that's the case for example H. Anything on example G there? We're looking good on that one. So in example H here, they're asking you to find f of g of 4. So we're going to start out trying to find g of 4 first. G of 4. So we're going to look at the function for g. That's this one right here. You typically work from the inside out with these functions. So see if you can't find g of 4. And whatever g of 4 is, then we're going to put that in for f. And then find that as well. I think I gave myself a little more space here than I needed. Okay, g of -4. Griffin, what did you get for, or g, not -4, g of 4. What did you get there? Let's see here. 1, 2, 3, 4, right? So that's g of 4, or that's 4. What would g of 4 be?
3.
Yeah, g of 4 seems like it's a 3. All right, let's go with that. And if g of 4 is a 3, let's put it into f and find f of 4. Aurora, what do we get for f of 4? It's going to be f of 3.
0.
Yeah, 0. So the graph crosses the x-axis right at 3, so we get f of 3 is a big goose egg. Nice. All right. I'm just going to do one of example I. This is a good example, and this one is directly taken from WebAssign. So, and I guess what I like about it is that it asks me, do you understand something, without really giving you a complicated problem. Let's work on g of f of 6. So this table gives you all these different values for f and for g. When you're evaluating g of f of 6, going to start with what's inside, f of 6. So how am I going to find f of 6? We'll find x equals 6 up here, and then drop down, you'll find f of 6. F of 6 is 3. So let's put that in there. That's a 3. Now that I found f of 6 is 3, then I can plug that in for g. So g of 3. And who haven't I heard from in a while? Leo, what's g of 3 going to be, please?
1.
1, 2, 3. There's x equals 3. What do we get for g when x equals 3?
4.
There we go. So g of f of 6 gives you a total of 4. Nice. You okay with that? All right. Do you want me to do one more example, or are you okay with these kinds of things? You're okay there? All right. Last but not least, right now I'm teaching calculus on Mondays and Wednesdays, and I guarantee when we hit section 3.4, some of the people would wish that they could do some review on some of this kind of stuff. What we have here is really the composition of two functions. And the goal here is for you to find those two functions and be able to write it in such a way that this is what you get when you put together those two functions. Now, when I look at this function, I see those two functions because I've been doing this for a long time. But let me help you try and get at that as well. The big picture is that on the outside of this, I've got the reciprocal function. Now, maybe I should use f and g like they suggest here. So the outside function that I see, the big picture, when I zoom out, I get f of x is 1 over x. And then when I zoom in inside, then I see that the little function is x plus 1. So that I'm taking the reciprocal of this function. Now if I put these two functions together and form g of x, the f of little g of x, let's see how that works out. Does it give me what I expect? Well, on the inside here, g of x is really just x plus 1. So I'll replace g of x here with x plus 1. Now let's look at the function for f of x. Function for f of x says, oh yeah, let's take the reciprocal of this. So the reciprocal of that is just going to be 1 over x plus 1. Nice. And that's what you're looking for. You're looking for two functions that when you put them together in the right order, it gives you this thing right here. So it's a matter of deciding, well, what's the big picture, what's the outer function, what's the inner function. It's not something that you're going to become a pro at overnight, but it doesn't hurt to look at this stuff now so that you're not going to be thrown for a loop when you look at it in calculus. I assume most of you are going to calculus, otherwise you wouldn't be in this class. Last but not least, example K here. Taking a step back, can anyone help me decide what the outside function is? What's the big picture? When you're looking at this, what's the big picture function here? When you zoom out, what function are you looking at? Yeah. The outside function, when you zoom out, if you lose some of the detail inside, that's okay. You're still looking at the absolute value of something. So the outside function is the absolute value of x. How about the inside function? What's the inside function? Any thoughts there? yeah, 1 minus x to the fourth. Thank you. So 1 minus x to the fourth. And when you put those two functions together, 1 minus x to the fourth, bam, you get this function. H of x equals f of g of x. And that's nice. Okay. Whew.